Hi, welcome back. We're up to lecture 19, and the topic of today's lecture is chi-square tests. In the first segment, we'll cover the chi-square goodness of fit test, and in the second segment, we'll cover chi-square's test of independence. So this lecture is divided in just those two segments. In the first segment, we'll talk about the chi-square goodness of fit. Up to this point in the semester, all of the analyses that we've covered in the course have assumed that we have a continuous outcome variable or dependent variable in experimental research. So typically the outcome variable was an interval variable or a ratio variable. Well, what do we do if the outcome variable is categorical? For example, if it's a nominal variable. Well, there are lots of examples of that. So if we go back to the beginning of the course, that first lecture, a diagnosis of polio, if we looked at it at the level of individual children, that would just be positive or negative. You're either diagnosed with polio or not. That's a categorical outcome. A place where this is very common, this type of research, is in psychology and law, where we're trying to predict whether a juror will vote guilty or not guilty, or guilty or innocent in a trial. Another place where this is very common is in election polling. So when we poll before important elections, we want to know how a voter is going to, which candidate they're going to choose, candidate A, candidate B, candidate C, and so on. Again, those are categorical outcomes. So as I said, we're going to talk about two types of chi-square tests in this lecture. The first one is the chi-square goodness of fit statistic, and the second one is the chi-square test of independence. Both can be used in either experimental research, like in the polio vaccine study, or just in correlational research, like in the election results. We're not manipulating anything, we're just observing how people are going to plan to vote. So the chi-square goodness of fit statistic, it just determines how well a distribution of proportions fits an expected distribution. So in election polls, is there a statistically significant difference in voter preference across the candidates? The chi-square test of independence determines whether there's a relationship between two categorical variables. It determines if there's a contingency, and you'll hear that phrase contingency table. So in the election example, we could look at whether there's a relationship between the gender of the voter and the candidate that they prefer. So I'm going to use an election example throughout this lecture. I live in New York City, and currently there is an election going on, or coming up, for a new mayor in New York. And assume I wanted to conduct a very small poll to see how, say, my neighbors intend to vote in this upcoming election. So right now, some of the leading candidates are Christine Quinn. She's the overall leader. Joseph Lota is another one of the leading candidates. But there's several candidates in the field right now. It's still early. I'm filming this in August. The election doesn't take place until November. So that's lots of other candidates. So I just put in an other category. So let's assume we just asked 60 New Yorkers who are planning to vote this November, who do you intend to vote for? Quinn, Lota, or someone else? And let's assume that we got these results. So 23 for Quinn, 12 for Lota, and 25 in the other category, which is about representative right now of what people are thinking in New York. If we're doing a chi-square goodness of fit statistic, the null hypothesis assumes that there are equal proportions across those categories. So it should be that there's no effect, that we can't detect a difference between the candidates. The alternative hypothesis is that we'll get unequal proportions. The chi-square statistic, this is the formula for goodness of fit. What we do is, a lot like all the other test statistics that we've covered in this course, is we basically look at the observed proportions relative to the expected proportions under the assumption that the null hypothesis is true. So we'll look at those numbers. Degrees of freedom in the chi-square test of goodness of fit is number of categories minus 1. And of course, the p-value is going to depend on the actual chi-square value that we get and degrees of freedom. So just like we did with the t-test, we had the family of t distributions, and the f-test, the family of f distributions. We now have this family of chi-square distributions. Again, we're assuming that this comes from a sampling distribution, and these sampling distributions differ depending on degrees of freedom. So that's what all these different curves are. And the degrees of freedom here are determined by number of categories. Again, it's number of categories minus 1. Since this is a NHST, null hypothesis significance test, we're also going to supplement that with an estimate of effect size. And the way to do that with a chi-square goodness of fit is to look at Kramer's V, or Kramer's phi. And the way to calculate that is to take the square root of the chi-square over sample size times k, number of categories, minus 1. So let's now do the math for this example. That's why I made the number of people that were sampling very small. I only sampled 60 people just to make the math real simple. So under the null hypothesis, we expect no effect of candidate. So the expected frequencies in this example should be 20, 20, 20, because I had 60 people and 3 categories. So those are the expected, this first row. But what we observed is down on the second row, we observed 23, 12, and 25. So now all I have to do is plug these numbers into that chi-square formula, get my chi-square, obtain my p-value from the right sampling distribution of chi-square, and then make a decision to reject the null or retain. So again, here's the formula. I've set it up in this table so we can do the calculations pretty easily. So we have the observed frequencies, the expected, again it's just 20, 20, 20. In the third column, I did observed minus expected. I could check my math just to make sure the sum of those is 0. I then square those, and then if I sum those, it's the sum of the squares, I get 4.9. That's my chi-square. So a chi-square of 4.9 with 2 degrees of freedom. If you look in the sampling distribution for 2 degrees of freedom chi-square, you get a p-value of 0.09. So not quite statistically significant. So that trend that looked like LODA's not really as popular as Quinn and all the other candidates combined, it's not statistically significant at this point. So while we could say that it looks like Quinn has a slight advantage over LODA, it's not a statistically significant effect. And what that means is, you hear this in polling results, they're still within the margin of error of one another at this point. If we wanted to, we could look at the effect size for this. Again, I use Kramer's phi. It comes out to be about 0.2. And this can be interpreted just like a correlation coefficient or standardized regression coefficient. A 0.2, it's sort of a weak effect, right? So again, this slight preference that we see for Quinn and other candidates over LODA, it's close to being statistically significant. There's a modest effect, but it's not a strong effect, and at this point, not statistically significant. I need to say a few words about how to set this up in R. We'll do this in the next lab, but you'll typically see a data frame that looks something like this, where again you have one person represented per row. So we have voter ID number, just give each person a number, 1, 2, 3, 4. They're each represented by row. And then in the second column, I just put down what candidate do they prefer, Quinn, LODA, or other. And then I also put in gender, because in the next segment we're going to use gender to look at, to see if there's a relationship between gender of the voter and their choice. In order to do this in R, to get the chi-square tests, we have to put those results into a table. And the way to do that is through the table function. So my data frame was called election, and what I want to table are the candidate choices. So if I put those into a table and call those my observed, and then run the function chi-square test on observed, then I would get the following output. And this matches exactly what we got for our calculations. The chi-square is 4.9, degrees of freedom is 2, and the p-value is 0.086, rounded up to 0.09 is what I got in my hand calculations. So to wrap up this segment, chi-square tests are used when we have a categorical outcome variable and as well categorical predictor variables. The chi-square goodness of fit statistic is an NHST, so we want to supplement that with an estimate of effect size. The way to do that in chi-square is Kramer's V or Kramer's phi.